Hey guys, we're going to take some notes about current and resistance, which is the next part of the unit on circuits. So this is what the first half of the notes packet page ought to look like. So make sure you are on this page before you go any further in the video. So to begin with, I want to define a couple of terms, and then we're going to look at some pictures and things which are going to help sort of illustrate the concepts. So current in general is the flow of charge through a material. We're not talking about charge, say, necessarily building up on something, such as on a capacitor, just usually moving in and out. But it could also be charge accumulating on surfaces, such as for a capacitor. All right, this notation, if this is confusing you, that's derivative. We could also say that current is just simply charge over time, and that's fine. Saying it that way is going to give us the unit of coulombs per second, as it says there. But generally speaking, we are going to call that an ampere, or amp for short. If you're thinking back on what we have said about the coulomb before, how coulombs, coulombs are big. Like I said, 1 coulomb is like a lightning bolt, okay? So if I'm saying that current is a coulomb per second, right? 1 amp is a coulomb per second. And you're thinking, wow, a coulomb's a lot of charge. I bet 1 amp is like so much current. Well, actually, 1 amp is not actually all that much. If you have, say, something like, oh, I don't know, a toaster, or maybe a sliding compound miter saw, those kinds of things might use what will seem to you like an incomprehensible amount of current for right now, such as, oh, I don't know, probably 10 amps or something for the toaster. I'm kind of making that number up. But the saw actually said on the side that it pulls 15 amps, which means that you need to hook it up to an appropriate electrical cord because otherwise you might start fires. Okay, so 15 amps is actually not unreasonable. And if you start getting into things like automotive stuff, you know, cars when they are starting draw hundreds of amps from the battery. So when something has current moving through it, you got to remember that that something is made of atoms. So here I have drawn on this object here, whatever it is, some conductor, I have drawn some of the nuclei. Not even close to all of them, just, you know, my favorite nuclei, I guess. And then, of course, there's some number of electrons, right, whatever. I have not drawn an equal number of each of those two things on purpose, right? If the plus things are a nucleus as opposed to an individual proton, there's a lot more individual electrons than there are nuclei, because, for example, if this is, I don't know, sodium, for 1 sodium nucleus, there's 11 electrons. Okay, fine. So a whole bunch of electrons, and in what's called the sea of electrons model in chemistry, those electrons are sort of freely shared amongst all of the various nuclei, meaning, you know, they can be traded around willy-nilly, and none of the other atoms really care about it. Now, normally in a conductor, those electrons are just sitting there, unless they have some reason to move, and they will move around if we do something like attach a battery to it. Now, if you're not familiar with this notation down here, this right here, that is pronounced EMF. What's EMF, Mr. Erico? EMF is short for electromotive force. People say electromotive force, and they say EMF, and use that symbol all the time to indicate the volts provided by the battery. A battery's entire job is to push charge around a circuit. That's what it does. So it's like a force, good enough. So by providing volts, the electrons now have a reason to start moving around the circuit. The other bit of notation that I put in here is a switch. And of course the battery symbol itself down here. So that's a battery. The switch right there is in what would be called the open position. I'm sure you guys have lots of switches in your house, and you know that if you open the switch, the lights turn off. But if you close the switch, then the lights turn on. Okay, great. So when I close the switch, now all of a sudden current can flow. That letter I right there is the symbol for current. Now, if you recall, the positive terminal of the battery is the one on the left side, and conventional current flow indicates the direction of the flow of positive charge. So by saying the current is to the left, which is always the way that it flows through the battery, not left necessarily, but from minus to plus, okay, which in this case is left, that would be the direction that we're saying that positive charge is flowing. Okay, so at this point, you should break to your notes packet and write something down. Conventional current flow follows the direction of, we said, positive charge. Write the word positive, please. All right, but of course, in most cases, the charges actually moving in the wire are going to be electrons. So you should write the word electrons in this gap right here. So that means that while we are saying that the current would be to the left here, the actual motion of particles would be electrons moving to the right. Okay, so there we show it, the electrons moving, in fact, to the right, through this part of the wire. All right, now, of course, up here in the wire, the big wire I drew up the top, the electrons are ultimately going to be flowing that way, and then they'll come back around the other side, and there we go. It's always going to be in a loop, right? Now, if you're thinking to yourself, loop, is there a better word for that? Yes, in fact, it's a circle, which is in fact where you get the word for circuit. The current always has to have what's called a complete circuit in order to flow at all, which is why when I drew the circuit with the switch in the open position, no current can flow. Soon as you shut that, or as soon as you open that switch, the current has to stop once again. So it's not like some of the electrons are going to keep flowing anyway until they realize, oh no, there's a broken switch. They just don't flow at all. If there's a broken connection anywhere, all the current stops flowing everywhere within that section of the circuit. Now this brings us to the term charge carrier, which might not be in all of your packets, but the charge carrier is the charged particle that carries the current. We said most of the time that's going to be electrons, but not all. Maybe in chemistry you remember the demonstration where they take a light bulb with some, like a battery hooked up and then some open leads, and then you put those wire leads into a salt solution, and lo and behold, it turns on. Now, I'm not going to try to find an image of this for fear of using someone's copyright image and then having my whole video nixed, but you can Google something like, I don't know, light bulb salt water chemistry demonstration, something like that. And in a salt solution, the charge carriers could be multiple things, all right? So it's the particle that carries the current, and most of the time that's going to be electrons. But in a salt solution, it could be, for example, if I mean literally salt, it could be the Na pluses and the Cl minuses as well. So really it's any kind of a charged particle, because any kind of a charged particle is a charge and therefore can be a charge carrier because it's got to be charged. All right, now the next term that we got to look at is drift velocity. Drift velocity refers to how fast those electrons are moving through the conductor. All right, so you can do a brief experiment here, okay? Stand up off the whatever surface you're probably sitting on, since I'm assuming you're sitting down, and turn the light switch on and off a few times. And I want you to see if there's any kind of a noticeable delay. Now there could be if you have something like fluorescent lights, okay, but if you have something like a classic incandescent light, there's typically basically no delay, which is kind of remarkable, right? And so that makes you think like, wow, I mean, how fast must the drift velocity be in order for the lights to just like, boom, instantly go on? And actually, believe it or not, the drift velocity, I'm going to demonstrate to you exactly how fast the drift velocity is. Here you go. I'm going to put the pen down here, and I'm going to creep. There you go. That's how fast it moves. Really, Mr. Erico? Yeah, I'm not joking. That's actually how fast the electrons are moving through the wire. It's like literally a snail's pace. Actually, it's slower than some snails. So what's the deal, Mr. Erico? How can it be that like the light immediately turns on as soon as I close the light switch? It doesn't seem reasonable. So the reason people often are thinking that like it just has to be so fast is because what they are imagining is this. If here's the switch down here, right? And this, what I've drawn up here, the conductor is actually a light bulb, right? Here it is, a light bulb and a bright light. Okay, right. I think what a lot of people are imagining is happening is that as soon as I close the switch, that the electrons that were in the battery or just like waiting right here at just before the switch are like they're poised and waiting, and then as soon as you close the switch they go wow all through the circuit, and that's not actually at all what happens. It's more like the water in a hose, okay? Take a hose that is completely filled with water and then turn the tap on. There is, you will notice, basically no delay between when the water comes out and when you turned it on. And that's not true if it's an empty hose. You got to start with a full hose. But the reason, of course, that it's like that is, well, as soon as you turn on the water pressure, all of the water in the hose starts moving at the same time because the the water in this analogy that's right here, just before the tap, begins to move as soon as you open it, which pushes all of the other water that is right here. And so all of it begins to move at exactly the same time. All right, so when we talk about drift velocity, don't imagine those electrons just flying through that circuit because that's not actually what's happening. They're really actually creeping along at a snail's pace or slower. But it is in fact the case that the lights turn on instantly simply because that wire is full of electrons and they all start moving at exactly the same time. Now for this next part, I'm going to refer to a game called Plinko, which a lot of people, when I say, anybody know about Plinko? They're like, I don't know what Plinko is. But you've all seen Plinko, or most of you have seen Plinko somewhere before, right? So to the right, here's a little picture of a Plinko board, right? And in this analogy, I want you to think about the electrons that are moving through the conductor as having to navigate this hazardous set of pegs that are in the way. All right, and those pegs are the nuclei, right? So here it is trying to move through this way, all right, because it's being pushed by the battery, but then it goes donk and hits a peg and it has to fall, and then donk, it hits another one, and then a donk, and it, okay. And so there's not really a clear path through the conductor. Even though it's a conductor and has a low resistance, it's constantly running into things, okay? So we will talk about this difficulty of getting the charge through as the resistance, okay? So I made a little animation so you could see sort of Plinko in action, more like how it would look in a real conductor. There we go. Look at those electrons flying through. Now, if you watch, occasionally one of them's going to hit a nucleus and bounce off, and that slows it down a little bit. And so because those nuclei are in the way and not necessarily in a well-organized fashion getting in the way, the electrons have to slow down, and therefore the drift velocity is small, and so the conductor has some amount of resistance. No matter how good of a conductor it is, it's going to have some resistance unless it's this special thing called a superconductor, which I will only really refer to right now. Superconductors have zero resistance. In other words, charge actually flows freely through them, which is kind of a crazy idea. All right, I think that's about enough information for one video, so let's go ahead and break to a part 2.